This is the first day of our 4-day Net Zero Research Conference. The first 2 days of this conference are structured around the themes of Network H2, which is the network for hydrogen fuel transportation, which is funded by EPSRC and led by myself here at Durham University. Network H2 brings together researchers, companies, government, and other stakeholders across the UK, and also interacts internationally with leading organizations and researchers in the transport field. The network is organized around 8 themes. Firstly, the whole transport energy system. Secondly, around pathways to sustainable hydrogen production and distribution, compact and lightweight hydrogen storage, compact and lightweight onboard energy conversion devices, lightweight electrified powertrains, hydrogen compatible materials and safety, multimodal transport and logistics and autonomy, and finally policy, economics and societal impact. The network is funded by EPSRC and was awarded so that we could act as a forum to maximize the impact of research that's being conducted, foster communication, share best practice, and disseminate information and data on hydrogen-fueled transportation research projects. Also tasked with capturing state-of-the-art in the area and identifying the research challenges, incentivize and barriers that exist, target our feasibility funding towards new cutting-edge projects, which will enable us to unlock collaborative research in this field, provide a wider forum for all stakeholders and all modes of transport and technology developers to be able to foster long-term collaboration between themselves and with new partners and new international research teams. And also to engage with the wider research community across physical sciences, social sciences, and engineering disciplines to maximize the dissemination of and impact of research outcomes and stimulate knowledge transfer between academia, industry, government, and all the other stakeholders. That's the remit of Network H2. So over the next 2 days, we will look at the challenges across the different transport modes, as well as the wider energy system required to support the hydrogen transition. Today, in its structure, it's organized in 3 parts. So session 1 will look at aviation and maritime sectors. We will then host a net zero question time panel with questions that have been provided by yourselves, the participants. After that, we'll have a lunch break, and then we'll resume with a session looking at road, rail, and freight. We have asked each speaker to present for around 20 minutes, and once they've finished, we'll have a joint Q&A session, and we're looking forward to listening to our speakers and hearing your thoughts on what they have to tell us. These discussions will help the network to shape our future research and our activities, so it'll be really very valuable to have your contributions and your feedback. So without further ado, we will move into our first session, and I'd like to introduce our speakers. Our first presentation is on aviation and will be given by Glen Llewellyn. He's Vice President, Zero Emission Aircraft at Airbus. He is responsible for all company-wide hybrid and electric propulsion research, focused on bringing zero emission flight to reality. Our second presentation will be given by Charles Haskell from Lloyds Register. He's been working in various ship repair and new construction yards in the UK, France, and Poland, and also working in South Korea on a number of projects on container ships, tankers, LNG carriers. He has led business development teams in the Middle East and Africa, and now in the UK. And he has worked with many zero emission projects and is helping shipping to decarbonize and achieve the IMO 2050 ambitions. So that's the introduction to our first two speakers in this first session. And so over to Glen for his presentation.
Good morning, everybody. Pleasure to be with you this morning and looking forward to taking you through what Airbus's plans are to bring a zero-emission aircraft to market by 2035. The first part of the presentation, in the first part of the presentation, I'd like to share a little bit about why we're doing this, give you some of the context, then I'll talk about the technologies and the aircraft, and then a little bit at the end about the timeline and what we're expecting to achieve as we progress through the next decade. So in terms of context, I guess many of you will be aware that society needs to significantly reduce its climate impact over the coming decades in order for us to meet the Paris Agreement. In terms of aviation, the aviation industry has set itself ambitious targets to play its part in contributing to success. We believe that we need multiple pathways to be accelerated in order for us to get there. There's no silver bullet. There's no single energy carrier or technology type that's going to allow us to solve the complete challenge. Biofuels, as many of you have perhaps heard about, are going to be important. But on top of biofuels, we believe, based on our assessments, that we need synthetic fuels based on renewables in order to allow further scale up and acceleration towards the meeting of these targets. If we go into a little bit of detail about what this could look like in terms of an energy roadmap for aviation, you can see along the bottom the timeline towards 2050. You can see biomass-based fuels being relevant along this time frame. In fact, our aircraft are already certified today to carry up to 50% of biomass-based fuels, and really what we need is the energy supply ecosystem, the regulation in terms of incentives to be put in place really for much more scale up than what we've seen over the last few decades. Then, in addition to these biomass-based fuel pathways, we need renewable power for aviation, and in the very short term, we could be operating direct air carbon capture facilities for the purposes of sequestration. We think that that's necessary in order to scale up direct air carbon capture technology, which would subsequently be used as an ingredient in synthetic fuels. Our aircraft are already certified to carry synthetic fuels up to the same 50% level as with biomass-based fuels. Then we start to talk about hydrogen, because hydrogen is a key ingredient for synthetic fuels. We definitely need hydrogen even for the existing fleet or for long-range aircraft, which, let's say, hydrogen in its raw form will not initially address. And then you see the top bar on your screen, which is really about the usage of hydrogen in its raw form in aircraft. And why we're interested in that compared to the other pathways are really down to two main reasons. One, we believe that the hydrogen aircraft have the potential to have a lower climate impact compared to all the other pathways. And number two, we believe that we can have a more economic aircraft, and where we have more economic solutions, we can have a more significant fleet-wide influence and reduction in an overall fleet-wide context of climate impact. And most of the discussion, most of what I'll share today is really about the hydrogen pathway for aviation. Once we start to talk about hydrogen, especially from low carbon sources, we need to look at what's happening in the renewable energy sector. I guess many of you will be aware that for sure in absolute terms, renewable energy is not where we would like it to be in order to meet the Paris Agreement. But nonetheless, there's a success story underway in the renewable power generation sector. World solar electricity production multiplying by 5 over a 10-year period. The world wind electricity multiplying by 2 over sort of similar timeframes. What we see happening in this field is very accelerated growth, and bear in mind that this is pre-COVID, this is pre all of the initiatives which are there to grow back green. This is pre the 2019 and 2020 period where many regions and nations have put in place even more incentives, even more regulation, encouraging these industries to grow. So our view at Airbus is that these methods of producing power are going to go exponential over the next decades. And we want to position the aviation industry to be powered by this renewable energy. The increase in scale that we've seen on the previous chart is essentially resulting in a decrease in cost of the electricity which is created from these energy sources. It's been quite significant over the last decade, and this is what is going to happen, we believe, into the future. We're going to see increasing scale. We're going to see increasingly competitive supply chains. We're going to see increasing investment in technologies which allow increases in efficiency and therefore continued reduction in costs. And as I explained earlier, hydrogen is of interest because when we look at cost of avoided ton of CO2, hydrogen looks extremely competitive, including the fact that we have to liquefy it, including the fact that we need to transport it, which is more complicated than some of the other energies in a future ecosystem. And if we look more globally and sort of zoom out and say, well, where are we today and where do we need to get to by 2050, not just for aviation, but as a global society, then really we're at the very, very beginning of this transition that we all need to make. The growth curves, the cost reductions that I've just shared are what has happened in the period more or less between 2010 and 2020. The growth that we're going to see, that we all want to see going beyond 2020 into 2030, 2040 and so on, is going to be massive. And that's going to increase availability of renewable energy. And because there are several industries that will rely on hydrogen for reducing its climate impact, we believe that it will increase the availability of hydrogen. And if we look specifically at the hydrogen ecosystem, there are lots of, there were already lots of initiatives supporting the development of a hydrogen ecosystem in 2018. This is a picture looking at what policy support for hydrogen was available in that timeframe. And what we see now in 2021 is 8 hydrogen truck concepts in development, more than 5,000 hydrogen refueling stations announced or planned. We see SAIC Motors in China developing 10 hydrogen cars to claim 10% market share by 2025. International Council on Clean Transportation suggesting that hydrogen could fuel approximately 99% of trans-Pacific voyages. The first hydrogen fuel cell ferries have been launched in November 2020. And this is going to mean that hydrogen as an ecosystem is going to scale, is going to be much more relevant. We can basically turn every corner today in society and see fossil fuel filling stations. We have fossil fuel in almost everywhere. That needs to be replaced by something, and certainly part of that replacement is going to be, we believe, by renewable energy and hydrogen. And that is something that we need to strongly take into account as we prepare our plans for the next generation of aircraft. If we look then specifically about how hydrogen can be used on board aircraft, we have the synthetic fuel pathway, which is compatible with existing aircraft and will be the solution for another period for long-range aircraft. We have hydrogen combustion and hydrogen fuel cells. And hydrogen combustion and hydrogen fuel cells, with the technology maturity that we're planning by 2025, we believe could be capable of powering 100-seat to 250-seat powered aircraft, 1,000 to 2,000 nautical miles. So very significant market that could be covered by, let's say, raw hydrogen propulsion system aircraft. These are the aircraft concepts that we revealed in September last year. The three concepts on the left of your screen show a turbofan configuration, a turboprop configuration, and the one in the middle is a blended wing body. It's probably the one that the media has published the most, but I have to say it's the most unlikely concept that we'll take to market by 2035. For sure, it's interesting in the longer term because this sort of shape has naturally lots of volume inside it. Hydrogen, one of the challenges of hydrogen is that it requires lots of volume to store it. So you can essentially have within a very aerodynamic shape your hydrogen storage. Nonetheless, it would be too much for us to change disruptively the propulsion system and the airframe design in one step. And so what we're looking at for an entry into service by 2035 is something more similar to the classical tube and wing configuration, but nonetheless with a very different propulsion system on board. We also released this concept in December last year. This is a fully fuel cell powered aircraft, whereas the three previous concepts have gas turbines on board. We're still assessing the scalability and economics of such an aircraft, but it looks like an interesting concept to be explored further in terms of climate impact, because we don't have any combustion happening on board the aircraft, and contrails also can potentially be completely eliminated with this type of concept. So one that is under exploration. Some of the technologies that are on board these aircraft. So I take an example of one of the concepts, which is a hydrogen combustion concept with a hybrid electric component. We have hydrogen powered gas turbines. These have been flight demonstrated already. In the 1950s, a B-57 in the US Air Force flew with a hydrogen powered gas turbine. A Tupolev 155 flew in the 1980s with a gas turbine with hydrogen combustion. So in terms of technical feasibility at the most fundamental level, this has already been demonstrated, but we have some work to do in order to take that starting point and develop technology which is acceptable for commercial aviation standards. On the liquid hydrogen storage side, you can see we have two tanks to the rear of the aircraft. There are two because we require independent sources of fuel for takeoff due to certification requirements. These are twin-walled vacuum insulated tanks. They're essentially a technology which has been demonstrated already in the automotive industry. There was a limited series passenger car using these tanks in 2010s. but we have a lot of work to do to take that technology, scale it up to the sort of tank sizes that we're interested in for commercial aviation. Fuel cells, as soon as you have hydrogen on board the aircraft, fuel cells start to be an attractive way to convert hydrogen into shaft power, along with power electronics and electric motors. We recognize that one of the challenges associated with this plan is airport infrastructure and hydrogen availability at airports. So one of the things that we're working on with airports and with energy suppliers, and some of those collaborations have already been announced, but there are others in the pipeline, is working on decarbonizing ground transportation around airports with hydrogen already in the 2020s. Airports are heavy goods transport hubs. We know that hydrogen is sometimes the only choice of these sort of vehicles, like buses, trucks, some of the ground support equipment around aircraft. And so we're looking at scaling up the use of hydrogen at airports in order to get ready for hydrogen usage on the aircraft in the 2030s. Our overall timeline looks something like this. So if we start on the right-hand side, we have an entry into service targeted by 2035. This means that we need to have the product selection, the technology maturation, the flight testing of the propulsion system completed by 2025. We had in 2020 what's called the pre-program launch, and the project started in Airbus around 2017, 2018. Once we understood what the Paris Agreement targets meant for society and specifically for aviation. Airbus's ambition to bring a zero-emission aircraft to market by 2035 sets a very clear ambition for ourselves. It drives a huge amount of effort and prioritization in our company. And I think it's also a message to our ecosystem that this is something we need to push extremely hard for, and we need to try to succeed on. For sure, partnerships with technology providers, research institutes, energy providers, airports, and regulators are going to be key for success. We're having to work with players that we don't necessarily traditionally work with on projects of this scale, and our humility and our collaboration in respect of what is going to be required to manage such a transition is very important. If you think you can help us, I've left some of my contact details at the bottom there, and it would be a pleasure to engage in further discussion. Looking forward to the Q&A later to answer any of your questions. Thank you.
Thank you, Glenn. It was a nice overview from the aviation side, and there's a lot of synergies as well with the maritime side, which is good to see to address these challenges. Just as a very brief introduction, I'm Charles Haskell, the Programme Manager of the Lloyds Register Maritime Decarbonisation Hub, which is really set up to address the maritime sector challenge. And this is based on a lot of evidence we've done over the last 5 years. I'm going to go run through some of them in terms of the relation and the challenges to the maritime sector. So moving on is, where are we in the maritime sector? So the work we did before in conjunction with UMass is we looked at the Paris Agreement and how maritime can reach the Paris Agreement. Currently, the shipping industry contributes to 2.3% of global CO2 emissions. If left unchecked, this could rise to 10% by mid-century. This is in conjunction with, as a mix of the shipping industry increasing, but also other energy sectors decarbonising. So that's often used in context for the maritime industry, which is often slow to progress, to actually show that if nothing is done, then more and more spotlight will be put on the maritime industry. So the work we did is how do we reduce the CO2 emissions compared to 2008 levels by 2050. We looked at 50% and fully decarbonising as well. But if we stick to 50%, the research we did, energy efficiencies will not get us there alone. Shipping is probably behind the curve on energy efficiencies, particularly if we compare ourselves to the airline industry, where a very small percentage gain is often being met. Within the shipping industry, there's several technologies today that can be used, such as Flettner rotors, harnessing the wind, air lubrication systems, and even just-in-time arrival, which aren't being adopted in many sectors, which can be. And this is partly due to currently shipping is using the dregs of the refinery process. It's using heavy fuel oil, and fuel is cheap. So the incentive to use energy efficiency devices aren't there. But even with those, is in order to reach the 2050 ambition, is we need an energy transition, and we need net zero vessels on the water by 2030 in order to reach our 2050 ambitions. So what are the options out there? So looking at sort of the key factors here in moving away, biofuels are obviously an answer as a drop-in fuel. In terms of sustainability, but other sectors also utilizing these fuels. We're not really considering biofuels too much in Lloyd's Register in terms of long-term sustainability and reaching 2050. Other industries which are harder to abate, such as the aviation, will be taking up these fuels. We see the primary focus being on the electrofuels, particularly hydrogen and ammonia. But whatever is the case with the electrofuels, whether it's synthetic diesel, synthetic liquefied natural gas, hydrogen is the feedstock for all of these fuels. So likewise, in comparison to the aviation and all the other industries, we need that upscale in the renewable sector as well. Coming into the challenges and some of the work we've done to date, we've been doing a number of projects both on hydrogen and ammonia. The ships themselves can actually be designed and built without too many complications. We do technology is catching up, but likewise, to really get the true efficiencies, we do need an upscaling in terms of fuel cells and moving into solid oxide fuel cells, and then we can see the true benefits. But if we take the three left-hand sort of columns here, the resources, production, conversion, system integration, and bunkering and ports integration, that's in a direct synergy as well with the aviation sector, is our challenges there are the same. It's not about pushing the problem upstream. We need green hydrogen. And from that is we then need the production, conversion, and system integration. So again, the success of the maritime sector is going to be very heavily reliant, particularly on electrolyzers, reduction of cost of the renewable electricity sector. And if we're looking at synthetic fuels, is also a lot of advancements and reduction in cost of direct air capture. One of the key factors of this energy transition for the maritime sector is currently it is using a fuel that is cheap, abundant, safe to handle, and safe to store. And when we look at the alternatives moving forward, particularly with methanol and hydrogen, with hydrogen and ammonia, is we have none of those things. It's not abundant today. It's not going to be cheap. And it's not safe to store or easy to store. And that moves on to the next slide when we're talking about energy densities. Within the maritime sector, the vessels they're carrying their own fuel. We don't have the pipeline distribution. And some of these are on very long-term fixtures and they're carrying a lot of cargo. One thing the Ever Given has given us is a concept of a size of ship. So if you take the Ever Given going on a trade route from Shanghai to Rotterdam, it's about 12,000 miles. It's carrying 20,000 containers. And it's normally bunkering on once for the direct route. So we'll either need a lot larger fuel storage area. that in turn will mean loss of cargo, loss of revenue, or the industry needs to change its habits and refuel more frequently. And so the options are there, but there'll be a change in both design and operational profile. I'll move on to the next slide, because this is driven by economics as much as anything else. So the work we've done in the past, along with UMass, is we modeled fuel scenarios. This case here, which I've put up, is based on a bulk carrier, 84,000 ton deadweight, so probably about 250 meter long bulk carrier by 40 meters wide. And we looked at various energy scenarios. Now, this energy scenario is based on a high renewable electricity price, and probably not the case as we see moving forward. This study is a few years old now, and renewable electricity is coming down. But what it is showing us is that the dotted lines are the biofuels, and over time we're going to see a cost increase in biofuels as the aviation industry adopts biofuels, but also biofuels are not scalable to the size the maritime industry will require as well. But as the cost comes down, we'll see renewable hydrogen and even renewable electro-ammonia coming down in cost. And there will be a midpoint in the mid-2030s, even by 2030 potentially, where the electro-fuels will become cheaper than the biofuels. So what this is really showing us for decisions made today in the maritime sector is we need resilience and we need a long-term understanding of the costs moving forwards. But what we do know from those is that regardless of which renewable fuel will be cheaper, it's the cost of these fuels. If we looked at a levelized cost of production, is these are going to be 2 to 4 times more expensive than the fuels of today, which poses a significant impact for the shipping industry. And this is where we've looked at the various fuels. What we have seen is the electro fuels, so the e-diesels, electro liquefied natural gas or synthetic liquid methane. Their costs are going to be much higher as a fuel due to the levelized cost of production, particularly with direct air capture. And this is something a model will revise as technology changes on the upstream side. Hydrogen in its purest form is the cheapest to produce. However, it's not as energy dense, so therefore we'll have less storage. It's going to be very costly to store in bulk in liquefied form at minus 253 degrees centigrade. It's going to require technology in order to store it. Compressed form, certainly ocean going, is going to be too large. And this is where in the shipping industry in particular, ammonia has really sort of captured a lot of the headlines at the moment. It's relatively cheap to produce. It's air separation to capture the nitrogen, and then the Haber-Bosch process to create your ammonia. It's more energy dense than hydrogen. It's easier to store. It's minus 33 degrees centigrade. And it doesn't have the sort of ignition characteristics of hydrogen. However, it is a very toxic gas and therefore needs to be handled with care. But we do have learnings of ammonia within the shipping industry at the moment. It has been shipped extensively around the world, and it can even be used as a hydrogen carrier for transshipment. So rather than refrigerating hydrogen down to minus 253 degrees, you can convert it to ammonia as a more energy dense form and ship it that way and reform it at the other end. But this will all play into the economics moving forwards. But very much like the aviation industry as well, it's not one silver bullet. There's no silver bullet in this. There's no single one technology. When we look at the various fuels, we're very much moving from an industry which is 95% using heavy fuel oil and marine gas oil. So it's really I'd say a monofuel today, moving to a future where we're going to have a mix of fuels within the market. Because different fuel sources in the future will lend way to different applications. I haven't in here covered electrification, so battery technology could be deployed on short sea shipping, on small ferries. Small coastal traders could potentially use battery technology or hydrogen with hydrogen fuel cells. And deep sea shipping is tending itself more to ammonia at the moment. So we're going to see a blend of different technologies moving forward. But really, the catalyst to all of this is the ports and the way they play a part in this, and how they can also be the integration between importation and exportation of the fuels, but also supplying into the national, I would say, the national grid or the national transportation network as well. So to really sort of, as an overview for the maritime sector, I think first of all, it's an investment. We're going to be moving from an era of capex to opex. So at the moment, a ship owner's decision is very much based on the capex of the vessel, how much it costs to produce, construct, into an era where it's going to be very opex driven. We know the new fuels are going to cost 2 to 4 times as much as fuels to today, and that's really going to drive more capex into energy efficiency technologies and more of a behavior into energy efficiencies in both operation and technologies. But we do need a carbon price to level the gap between the fuels of tomorrow and the fuels of today, and that is lacking in the maritime industry at the moment from a policy perspective. So flipping to the right side here is we do need a strong policy interventions in order to lead the investments, because at the moment there's an investment risk into supply chains for renewable fuels for the maritime industry, but also the construction of port infrastructure and the vessels themselves is a risky subject. In terms of technology, we're currently involved in a project called the Castor Initiative, and we've got several other projects on the go as well, looking at the conversion of a MAN Energy Solutions 2-stroke engine to run on ammonia. And this is basically proved that the technology within the maritime sector can convert in about 4 years' time to run on ammonia for certainly a major engine distributor. So it's not so much of a technology challenge. There will be safety challenges which need to be addressed, and the maritime industry will need to go through a safety culture change, and potentially also a rethought in the way it designs vessels and to look at inherently safe design. But the bulk of technology challenge is really on land and the infrastructure and the fuel production. So our approach at looking at this challenge from the Decarbonisation Hub is basically looking at investment, technology in the community and the readiness levels of all those three, both today and moving forwards. And we're putting that into a model of a maritime solution readiness model in order that we can lead the industry forward and allow those decisions to be made to allow the investment to drive the technology moving forwards. Thank you very much.